We will study now an example of a Hilbert space coming from functions, periodic functions with complex values. And for this, we will show a particular very important Hilbert basis, which then we will make us write the periodic functions as series. Okay, so let's consider the following space. So L2, I read it like this, L2 complex of the interval minus pi pi, defined as all those functions from the interval minus pi pi into the complex numbers, complex plane, complex numbers that are measurable, of course, measurable, and for which the integral from minus pi pi of the norm square of the value is finite. And on this space, we will consider the scalar product defined as, so the scalar product between f and g, by definition, we prefer to have a normalization divided by 2 pi of the integral between minus pi pi of f times g bar. Bar is the complex conjugate, and I recall that having the complex conjugate, one can write the norm of a complex vector is of a complex complex number is z times the conjugate of z. This is the norm square. Okay. So a little comments about this definition, because now we are actually considering complex vector spaces, not just real. And what is the meaning of having a scalar product in this case? We have to be a little bit more formal. So note that, okay, so first of all, what does it mean that we have a space, we have a function, complex value that is measurable? Now, this is just the same of saying that we can write f as the real part and the imaginary part. So now these are real values and they are measurable, such that f is just the real part plus I is the imaginary number, times the imaginary part. Okay, in this case, the norm of f square is nothing else than the norm of fr square plus the norm of fi square. No, so this is a real number at every point. And the integral yeah, I will put the evaluation at the point, because I don't want people to think that, I mean, these are functions. So when you evaluate at a point, becomes a real number. Okay, and the integral of f, by definition, is the integral of the real part plus I, the integral of the imaginary part. And now this is a complex number. Okay, so now what does it mean that we have a scalar product? And so it's going to be linear in the first entry, but not linear in the second one because of this conjugation. But actually what is going to be is that the above scalar product and these are the scalar products that one considered in complex vector spaces. So is valued into C, it's a complex number, and it is not bilinear, but is what's called sesquilinear, i.e., now if you take complex number, and then if you multiply the first entry by lambda, then okay, the scalar product gets multiplied by lambda, but if you multiply the second entry, then it changes by lambda bar, and is not symmetric, but is what happens is that if you swap f and g, what you get, you have the scalar product of the conjugation. Okay, so whenever we have such a structure, we say that the space, so in this case L2C, with the scalar product, is a complex Hilbert space. So it's still complete in this case. Okay. Okay. End of the comments about the scalar products. Okay, now let's remark that this space of L2 is separable. So let's remark one thing, that so on L2C, so I mean L2C of minus pi, I cannot say the step functions are dense, but I have to consider the complex valued. The complex, the proof is the same of the real one valued. The complex valued step functions are dense, and on that hand, so the characteristic of a set can also be approximated by a characteristic of open intervals. Now, and this is because we are using the Lebesgue measure. Is upper regular. We can approximate it with open sets. So every measurable set can be approximated with open sets, and open sets in the real lines are just sum of intervals. So consequently, we have that the set. Now let's consider characteristic of intervals. Okay, it's the same if they open or close. AB, and we multiply by a complex number, so C plus ID. Okay. But now we can just let this number A, B, C, and D be rational. Okay, of course we have that A is less than B, and they are between minus pi and pi. This set is countable and dense. Subset of L2 complex minus pi. Okay, so this means that this L2 is separable, and therefore it emits a Hilbert basis. So what we understood is that L2C is separable, and therefore admits a Hilbert basis. Our plan is to next present one such Hilbert basis. So we next present one. So define for all k an integer number, the function key k bit from minus pi into c, the function k t to be e I k t. Now this is complex notation, complex I. So this is, if you want to in a complex and in a real and imaginary part, this is the same of saying cosine of I, cosine of kt plus I sine kt. Okay, so these are functions, and the theorem we want to get to is that this sequence of functions, this countable sequence, is a Hilbert basis for L2C minus pi. Okay, in other words, these are orthonormal vectors. That's easy to show, and their span is dense in L2. After this theorem, we will have the consequence of the properties of Hilbert basis that we saw before. So I'll write first the consequences. So the consequences are that whenever we fix a function, complex function in L2, and then we set the Fourier coefficients, okay, these are called Fourier coefficients. This is the scalar product between f k. So it's called Fourier coefficients. Then we have, so if we sum these coefficients multiplied by the functions ai, k, t, this function, okay, k goes from minus m, as m goes to infinity, in the norm in the topology of L2, this converts to the function f. Okay, second, another way of expressing ckf is, okay, now I just express the integral. Explicitly writing explicitly the definition, e minus I t and k t dt. And remember, here there is a minus because this is the conjugation of the second function. And the third property is that if we sum all the square coefficients, then this gives us the norm of the function. To norm of the function. This last property is, this equivalence here is also called Parseval identity. Okay, so these are immediate consequence of the fact that we are taking the coefficients with respect to a Hilbert basis. Okay, so but let's prove that this sequence form a Hilbert basis. So toward the proof of the theorem. So first of all, it's clear that these functions are functions in L2 And this is just right. One can write the norm, or better the norm square. This is by definition is 1 over 2 pi, the integral between pi, minus pi and pi of the norm of kt square dt. Okay, now this number here is a number on the unit sphere. Okay, so it's cosine plus I sine over the same element, right? So the norm is equal to 1. And then for when you integrate, you get 2 pi, and you divide by 2 pi, and this is equal to 1. Okay. 2, this sequence is orthonormal. Indeed, okay. We already have, they have unit norm. We just prove it. They have unit norm. And for all m different than k, if we consider the scalar product between kk and km, this is equal to 1 over 2 pi, the integral between minus pi and pi of e ikt times the conjugate of imt, so it's e minus m imt dt, which is the same as 1 over 2 pi, the integral minus pi pi, e I k minus m t dt. Now it's important now that this number is not 0, because this, the m and k are different. So now I can integrate, I can write a primitive of this function as ei k minus m t divided by k minus m t between minus pi and pi. And now I evaluate. So at pi, the sine is 0, the cosine becomes 1, so this becomes 1, and now same thing on the other extreme, so this is 1 minus 1 over k minus m. Where did I write? So here I wrote a t, it's not a t, this is a m and I. So I, okay, and this difference is 0. Okay, so they are orthonormal. For the proof that the span of this base of these vectors is dense in L2, we need a theorem by Stone-Weierstrass that I will present now without a proof. So for a proof that span of key k is in Z is dense in L2C, we rely on a theorem by Stone and Weierstrass. Before that, some terminology, some definition. So given a set, let's call it X, and a family A of functions from X into V. So a family of functions from X into a vector space V. So think of V to be the complex numbers. We say that that A is an algebra if it is, so when you have functions value into a vector space, okay, no, vector space is not enough. Let's do it value into the complex numbers, right? Because you need another algebra. Okay, so let's do into C. Let's do like this. Into C. So when you have functions value into C, what you can do, you can multiply by element in C, the function, you can add them, and you can multiply them pointwise. If these operations, they will let you stay within the family A, then we say that A is an algebra. So if it is closed under multiplication by scalar, under sum, and under product. So, okay. In other words, if you have two functions in A, then the function, let's do three functions, alpha, beta, and gamma in A, then the function and a scalar lambda in C, then the function x goes to lambda alpha x plus beta x times gamma x is in A. Okay. Okay, this is an algebra. And next definition, the last one, we say that A separates points if whenever you take 2 points of the space x, there exists some function in A for which the value at these points are different. And moreover, we say that alpha is closed under conjugation if whenever you have alpha in A, then the complex conjugation of alpha is also in A. Okay, these are the assumptions that we will have in the following theorem by Stone and Weierstrass. So suppose you have a compact metric space. Consider C0 the continuous complex valued functions. So continuous complex valued functions on K. And we take A to be an algebra of functions, of continuous functions that separates points, and three assumptions, contains the constant functions, and constant functions and is closed under conjugation. Then the conclusion is that A is dense in the space of continuous functions in the sup norm, i.e. for all f continuous functions on K, and for any epsilon, there exists alpha in A such that the sup between alpha of x, the distance between alpha of x and f of x, when x varies on all of K, this is less than epsilon. This is the Stone-Weierstrass theorem. Okay, now think that now if you consider alpha and f to be L infinity functions, then this is exactly the infinite norm of the difference alpha minus f. So it's the distance between alpha and f. Now we are going to have some observations about the family of that we want to prove to be a Hilbert basis, and what we want to consider. We want to define a family starting from here. Actually, it's going to be the span of this family. This is going to be an algebra that satisfies the assumptions of Stone-Weierstrass. So first of all, some very small observation. First of all, let's remind that so key k t, this is by definition, is E minus I, no, without the minus, sorry, I k t. All right, so first observation is for k equal to 0, then ai 0 t, so this it's constantly equal to 0, which is 1. Okay, so in other words, if you take lambda key 0, when lambda varies in C, then these are the constant functions. Okay, 2. What happens if we consider the algebra generated by these functions? First of all, I will observe that if you take key m times key k, then by the property of the exponential of exponentials, this is just key of m plus k, right? So in particular, so if you take key of 1 to the power n, this is exactly key n. 3, if you take the conjugation of key k, this is exactly key minus k. So what we get is that, so the algebra generated by key 1 that is closed under conjugation and contains the constant functions, this is exactly the set. Let's give a name, T, just the span of key k when k runs in Z. So this family here, this span, let's give a name. So these are what are called the trigonometric polynomials. So what I'm saying, so the trigonometric polynomials are the algebra generated by this key 1 that is closed under conjugation, and this is because, okay, it's because if you want an algebra, then you should be able to multiply key 1, so you get all the key n. But then closed by conjugation, you also have the one, and this is for n greater than 0. But then if you also want to have it closed under conjugation, then you will also get negative indices. And it's linear, so it should be a vector space closed under sum and multiplication. So this is the span, and actually what's important, this is a complex span. So with complex indices, this is what we are thinking. Very good. Right. So in other words, let's think that this is whatever key 1 generates to then use the hopefully use the Stone-Weierstrass theorem. So, but let's check that this algebra separate points. But actually, it's enough that to check, to use the generator. So, key 1 separate points. Separate points in our space. So, what is our space? Our space is, let's consider minus pi close on the left and open on the right. And this is because, you see, this function here is really injective in this interval. Remember that this is sine of t plus I cosine of t. So sine of t so you just argued saying that you can divide this interval into two subintervals. One is when sine is injective, and the other one when cosine is injective. So this now value into complex number, this function is injective, since key1 is injective. Okay. Right, it's not injective on the extremes because at these 2 points you have the same value. But then what we have to do, we have to now identify these 2 numbers. So we shall apply Stone-Weierstrass to the compact space that is minus pi identifying pi with minus pi. And this is just a circle, identifying the extremes of an interval. Okay, so we can apply to this, and so what is the conclusion? Is that for our f in L2C, and for any epsilon, we can take g continuous function S1 with value into C, such that f minus g in the normal 2 is less than epsilon. And this is because C0 compact support, but here now this is, in this case, it's the same of the continuous function because the space is compact. This is dense in LP, and now it's dense in L2. This is something we discussed already. Okay, and Now we use Stone-Weierstrass. Stone-Weierstrass implies that there exists alpha in the a trigonometric polynomial such that alpha minus g is in the sup norm is less than epsilon. Now, as a consequence, we have that, okay, so alpha minus g, as we said, now if we see them as functions in L infinity, then the norm is the same, alpha minus g, the sup norm. And now I claim that this can be bounded from below by the measure of the space to the power 1 minus 1/2, the norm of f of alpha minus g to norm. Okay, why this is true? This one is true because remember we proved that if the space has finite measure, then there is a containment in the L2 spaces. And actually what we prove is that the LP norm of a function is bounded by the measure of the space to the power, I think it was 1 minus 1 over p times the infinity norm. Okay, and of course, what is this? Mu of x is the measure of the space. Okay, but as measure, we are considering 1 over 2 pi, the Lebesgue measure of the space minus pi. Actually, we decide of normalizing exactly to have a probability measure, so in such a way that the space is as measure 1. Okay, so what we have is that the L2 norm of f minus g is bounded by this quantity, which is bounded by epsilon. So this is bounded by epsilon, this is bounded by epsilon, by triangle inequality, we have that alpha minus f in the L2 norm is less than epsilon. Okay, so we were able to approximate arbitrarily well every function in L2 with a trigonometric polynomial. So this means that T trigonometric polynomials form a Hilbert basis for L2C of the interval minus pi. Okay. These are functions that are very important because one can see the spaces as functions that are periodic, right? So it's like one can continue these functions periodically with period 2 pi. So what we were able to write, we are able to write every function as a sum of an infinite series of functions that are sinusoidal. They are trigonometric. Okay, and this should be seen as a function is written as sum of the frequencies of the functions. Right? So that's why this theory of Fourier series is important in many applications in physics and engineering.